Greetings, everybody. My name is Kevin Kotchak. I'm the founder CEO of Chemical Q Device. This is Thursday, September 12th, 2024 for 149 high dimensional and complex spectrometric data and analysis of an organic compound using large multimodal models and chain outputs. So I wanted to do the study to really stretch the AI models to see how well they perform with just a ton of data. So high dimensional data and complex data is known to be a difficult task if you're just doing things manually. But with AI models, they can either reduce dimensions or go about the problem a different way, mostly automatic in this stage. So basically what I'm going to pick up with here is part C. So part C is basically this. So 3.5 Sonnet, which is an AI model, their prediction was then further improved in part C by utilizing manual chained explanations of the spectra by the author to yield what is believed to be the correct structure with stereochemistry to the unknown problem. To the author's best knowledge, this is the first LMM, large multimodal model, to generate the C15H22O2 drug compound derivative S ibuprofen ethyl ester using high dimensional data from 13 detailed spectra, which I'll show on the next slide. The purpose of this study was to utilize cutting-edge natural language processing techniques to evaluate an advanced chemical structure consisting of IR, proton NMR, C13 NMR, depth NMR, COSY, TOXY, HMQC, HMBC, and NOSY with expanded views of spectra too. So what that looks like is basically this. If you ever took organic chemistry, this is more like graduate work here. And you've probably seen IRs a ton of time. And so basically you get these bands, these absorption bands. So what's shown here, and actually I was able to include the structure here. So it's basically ibuprofen instead of carboxylic acid at the left terminal. It's going to be ethylated. So S-ibuprofen ethyl ester. So we see the ester substituent. We see the chiral carbon here, a single chiral carbon, an isopropyl group, aromatic ring as well, with that ethylated portion of the carboxylated functional group. And in IR, there wasn't a ton to extract from. Basically, at this 3000 figure, it's a combination of CH, CH2, or CH3 stretches. And this, these two, and I counted this as the aromatic para substitution. And actually, you see the carbonyl resonance here coming from the ester at close to 1750, like at 1749. And I didn't spend as much time in the fingerprint region, but there's probably additional information in there as well. So what had happened is, I take all these spectra and I manually calculated, where all the resonances are, the chemical shifts, as well as splitting patterns too. For proton and then C13 depth. And then the 2D NMR, it's about correlations. So I did the correlations as well. And this was the structure that 3.5 Sonnet came up with. And I'm going back and I'm validating if this structure makes sense right now. And we see in the proton NMR, it's basically this, H22. And all of these made sense, right? So the two groups of aromatic protons, those are going to be 2 and 2. The diastereotopic protons, which is the CH2 to the left of the ester bond here, actually, it looks like, you can see the zoom right here. It looks like it's like 14 peaks, but there's kind of like a boundary in the middle. So I counted it as a doublet of quartets. And so that'd be 16. So it looks like there, it's probably some overlap in there. And, as far as some of these other ones, more downfield, that this one in specific, this triplet, this quartet, actually, sorry. This specific one would be next to the CH3 chiral carbon here. And then, going further upfield, the septet, seen as the CH. And the thing is that for part P of this, or part B of this specific manuscript, is that the original 3.5 Sonnet group did not have an isopropyl group. And this looks clearly like a septet, one hydrogen, and then this last one at 0.89, definitely integrating to 6, being these dimethyls of the isopropyl group. And then, we see some of these other CH3s showing up as well. So this all checked out as far as this was the compound that the AI model gave to me in this first row. And then likewise with the C13, we see that carbonyl way downfield from the ester group where it should be, not being that tall, which is stereotypical of that specific type of carbon resonance. And then the two C groups off the aromatic ring that are quaternary, and then we see the other CHs that are taller there, and then the solvent ring. And this next one would be, basically this diastereotopic carbon having the diastereotopic protons. And the depth also made sense. The only thing about this depth spectrum is some of the CH3 groups came down to the 90, so this depth 90 spectrum that's typically only for CH groups. So we see the CH2 groups on the bottom, and then the top would either be CH or CH3 groups, and then the CH comes down, leaving, the methyls up here on the previous depth. And the COSY, TOXY, GHMQC. So COSY is proton-proton, and all of these checked out. There wasn't really anything strange about it. TOXY gives longer proton-to-proton interactions, like within the same spin system, and those pretty much checked out, except for the isopropyl group, and they're known to do these things. If you have something like terbutyl or isobutyl, is you'll get some type of bleeding effect. And that was the only thing besides, the depth with a COSY 90. And obviously those are methyls because they're so upfield anyway. And I saw this effect with the dimethyl off the isopropyl in other types of spectra too, with some bleeding, especially with nosy, basically spatial interactions. So GHMQC and GHMBC, these are proton to carbon, GHMQC being shorter range and GHMBC being longer range. And I had to figure out basically, and the structure was already set based on what AI provided, but as far as assigning which carbon was which, and it does help to carry this through to completion, which is what I did. And I'll show you in the next couple slides of my exact carbon assignments and the exact proton as well. Now, these were derived from, it's Professor Nowick at University of California, Irvine. It's a final exam. It's actually an unknown. And, the manuscript, you can see this, it's currently up on ChemArchive. And in the supplementary files, I included all of these high resolution images if you ever want to run them to see if you can replicate this. Okay, so for prompt 4, so basically this is part C of the paper. I didn't touch as much with the part A and part B just because these results were the ones that I was looking for, and just do the sake of time too. So the prompt that I gave it, so in natural language processing or generative AI, and even more specifically for these large multimodal models or large language models, you have to give it some type of instruction. So this is the instruction I gave it. Provide the compound name and stereochemistry with annotated substituents based on the molecular formula C15H22O2, and provided data. Include all relevant information that was used to obtain your decision. So that's basically shown here in this first part of this figure. Is I took the spectra 2 descriptions, and then now, I chain them together, and then I'm giving it to some AI models, okay? In this case, there's 3. Then the prompt is executed, so meaning that the statement plus the data together, and a compound is generated based on the request in the prompt. So we see that here, I included the structure up here, S-ibuprofen ethyl ester. Now, the thing with 3.5 sonnet, like I said before, it was showing the most promise out of any other model, because in the previous step, the part B, which is in the manuscript there, in that specific step, it generated the same product 3 times. Although the data, because text is kind of king still at this time, and image analysis, there's, you need to have like more images to train off of, and more examples, and they're more complex to deal with than text anyway, is that it didn't have the isopropyl group. It had, it fulfilled the requirements. It's a 5 degrees of unsaturation that's shown here, 4 with the ring, and then 1 with the carbonyl. So basically, in this specific set, 3.5 sonnet, they all performed similarly, a little bit shorter response for 3.5 sonnet, which I'll show you. This is an AI model by Claude called Claude.ai. And ChatGPT 4o, a little bit longer, about 480. Grok 2 is by X.com, X Twitter, basically. And, basically these are submitted. Now the times for 3.5 sonnet and ChatGPT 4o about 19 seconds, which isn't that bad at all, to look at a bunch of spectral data that's been interpreted in text form. With the Grok 2, 46.7, that can change in an instant. So you see for out of these three, the 3.5 sonnet, which I also really like the structure, which I was able to verify on my own. As of today, a couple hours after I published this, ChatGPT announced that they're have a new model. It's called it's this new O1 model, and it's a preview to the next forms of ChatGPT. And when I plugged it in, it too came up with this same S-ibuprofen ethyl ester. That was not included in the manuscript. It was afterwards. But it's the same type of notion. Like we have high dimensional complex data coming from multiple different types of not only NMRs, IRs, C13 NMR, proton NMR, and then additional 6 spectra on 2D. This is like way beyond, I believe, what I did for my final exam. And although that was a tricky problem too when I was in school. So it's a very complex scenario that it really has to understand, spectroscopy and the relationships between, proton correlations and proton C13 relationships as well. So as of, later today, like I said, I was able to get the same S-ibuprofen ethyl ester response, based on the same data that I submitted to 3.5 and these other two. Okay. Now we see here, and this bottom one basically shows the compounds, and they correspond to the number of carbons. And actually, I get the compound, and then I use another service to get the molecular formula. So like I said, in all these, and I tested 8 models total in a different section in the manuscript, and 3.5 sonnet came out winning. And I looked at these, and I was like, for the 2D NMRs especially, in part A, it just was not delivering like the level of detail needed, especially from one of the models. And like I said, at this specific stage, it just wasn't enough to use image analysis through large multimodal models. However, text being fed into it and still being high dimensional and complex, it was able to come up with this appropriate response. So here's some of the assignments here. So again, this is the structure that was provided basically by AI, 3.5 sonnet. And again, it kind of went back and forth. Like I looked at the spectra and I figured out some things, but I wasn't able to piece it together all by my own initially. I went and ran it. And when I ran it, I was like, okay, this probably makes a lot of sense. And then I spent additional time, like I said, with these assignments here. So with the protons left to right, so it's methyl 1.2, distereotopic protons at 4.12. And again, these show up just slightly different ppms. And it's due to this electronegative withdrawing group here. Also this methyl at 1.48, hydrogen at 3.68. These are all making sense across the 1D NMRs, and then also with the 2D NMR spectra as well. Now, the way I figured how to actually get to this, I did a 3D model online, and then I also did another one, kind of like a physical model too, is that there was a correlation between this hydrogen and this methyl here. However, you see they're on 2 different planes. So this is proton coming out, this is methyl in the back. And according to this Kahn-Ingold prelog, basically this assignment is, the ester would be number 1, phenyl 2, methyl 3. So that would be R. Now, since hydrogen is not in the back on a dash, I had to flip that. So then this designation is S. So that's how I came up to that. And then we see the phenyl 2, and then we see the CH2. And again, there's just like that, correlation between this proton and then the two methyls off the isopropyl too. The carbons were a little bit trickier. I mean, these make sense too. The 1461, 175 being furthest down field. That's just typical. This 46 being the right after the 61, more upfield, and then the CH3. Now, the ones that were trickier were these assignments. I already had the structure, and it was just to further kind of prove it. And basically, I had these flipped, and it's sometimes you can get that with carbon. But basically, it was the only way I could fulfill with these assignments the difference between the GHMBC and GHMQC to fulfill both of those, being either one was shorter ranges in bond and one was larger. We see the CH2 and this methine. So again, across all these spectra, there was just a couple things with this isopropyl basically having interactions with many different parts of the molecule. So that's very typical. And, like again, with the diastereotopic protons over here, and then the nosy, which is the spatial arrangement, again, there's multiple ways to solve it, or using AI or doing it on your own. But it makes sense after doing all the spectra, basically manually. Now here's the response provided by 3.5 Sonnet. This is an AI model by Claude.ai. And out of everything tested right now, in part A of the paper, which I'm not going to cover as much here, it actually didn't finish the best because it didn't analyze 2D NMR too well. But on a text basis for chemistry, as of before I submitted the paper, and now with this O1 model that we have from ChatGPT, that's also got this answer too, in a similar type of output, but it's going to be different. So it went through a lot of the steps, with proton NMR and COSY, and you get a ton of information from the 1D spectra. And you also need to use the 2D spectra that I showed from before in order to get a lot of these, shorter range, like COSY shorter range, and like a TOXY is longer range, between protons. So, this information that it provided, makes sense. And basically, it talks about the stereochemical assignment too. And I was just very impressed, although I didn't get the first part with the large multimodal models producing the outputs, directly from images. Now, I would like to say in the manuscript before this, which is also up on ChemArchive that you can download, on that specific one, I was on a shorter, it only had 5 spectra. This is like 13. And it was a C9, I think C9H9N for that specific molecule. I was able to upload all spectra at the same time with a single prompt, with a single click. And 3 of the GPT-based models, I think it's Scholar GPT, GPT-4o, and one other one, is that they were able to provide the answer. Now, what was different about this one is it was so much more complex than a lot of the other examples that I came across. And when you're talking about high dimensional data, you're typically talking about having to pre-process this data on your own using principal component analysis, partial least squares, these types of methods. Now, when I asked the models themselves, 3.5 Sonnet and ChatGPT 4o, what would you use for this? They both responded similarly, like these methods like PCA and PLS. And then when I uploaded the data and asked him, 3.5 Sonnet wasn't as specific. It just said it would just do it, for this specific type of problem. And then the ChatGPT 4o said something like it's a problem-specific dimensionality reduction. Regardless, when you're dealing with this amount of data, and again, with part C, it was turned into text data, which is still a lot because I have to pick all these peaks, and there's just so many things to look at all at the same time. The large multimodal models in this specific case, or LLMs, Grok 2, I didn't have, well, actually, I think it can output images. Regardless, these models are doing some type of automated processing effective. And it's definitely a developing thing. And I would say out of all of these, the ChatGPT 4o, like I think several weeks ago, I upgraded the model, and I tend to even get better results. Okay. And then they double their image uploads from 5 to 10. So it's going to be some time, when there's broad utility of using, 2D NMRs especially just because, it takes more training data. It's just, there hasn't been nearly as many experiments for 2D NMR as there is for, one dimensional proton carbon. And there's other atoms too to focus on too. But that's the moral of the story here, is basically it's, there's a lot going on. There's, if you apply for a grant, they say we want a specific algorithm. And I think in large language models and large multimodal models, they already use many algorithms to get to this inference model, meaning for me to test it. And then they use other algorithms while they're, inferencing in order for me to get my data. So I don't really think that it's a specific, like, it's like one algorithm will save the world. It's like many algorithms that were used and are used in large multimodal models. And, basically where all this is going is that there's two ways of looking at this. Is you can either, fully trust the LMMs or the LLMs to do this processing of high dimensional data for you. You can sometimes ask them how they actually came across it, or you could probably even specify. So say if using PCA or using PLS, perform this high dimensionality, reduction problem using all these spectra, and that's something it may do. But the moral of the story is it's a huge thing, because high dimensions, across drug synthesis and medicine and all these types of things is a massive issue. And it's associated with, you have to make approximations. And it's also associated with a lot of skill and expertise in order to do each step correctly, that you figure less and less experts available to do these steps correctly. And there's paper after paper that use very manual techniques to address high dimensional data. So, just figure there's a lot of processing power, coming from these generative AI models that I use here. And, I'm more so in this case in automated methods. I didn't specify it to use a specific one, but I really think that this is the future of chemistry and drug synthesis. And, for medicine in general, is to either do automated approaches or specifically have these, hundreds of billions or over a trillion parameter models that are very substantial to do these things that, only skilled and expert types of data scientists can do well. Okay. So yeah, this has been Thursday, September 12th, 2024, 149, high dimensional and complex spectrometric data analysis. Again, this will be up on YouTube. Now, all three of the recent manuscripts are up. The first one is more general. It talks about using these types of software for an AI across many different use cases, reactions, synthesis, and then also kind of like, find this, biochemical enzyme specific information just buried inside a ton of data and a ton of text. And it does that quite easily. And, the second one was basically like this, but kind of scaling across 3 different data sets. And again, one of them, I actually got the correct unknown 3 times. And then this one, I believe the same case, but on a much bigger scale. And, with a single big problem. Again, thanks everybody for coming on. Have a good rest of the night and have a productive rest of the week. Take care. Bye.